Continuing with our doom and gloom theme from the volcanoes lectures, we're now going to take a look at earthquakes. This opening slide is an example of a structural failure related to the earthquake of Kobe in Japan. When we discuss earthquakes, we're going to talk about how earthquakes can be understood in terms of the basic mechanisms of deformation, the fact that most earthquakes occur at plate boundaries, whether they're convergent, divergent, or transform boundaries. That's where most of the action takes place in terms of earthquake activity. And unfortunately, earthquakes cannot yet be reliably predicted or mitigated, which leaves us in the same boat as the volcano predicting people. We're okay in a very loose sense. We know an earthquake's going to occur within maybe a couple hundred years, but that's not really comforting to people that are looking to move into an apartment on the 33rd floor in a place that has suffered an earthquake 50 years ago. So for this lecture, we'll discuss what is an earthquake. What does that mean, other than the shaking of the earth? How do we study earthquakes? How do we investigate the cause, the influence, the subsequent effect of a given earthquake or series of earthquakes? How do we define earthquakes in terms of their size and their relationship to different patterns of faulting? How do we evaluate earthquake hazards and risks? Is it worth taking a chance living in one place versus another when we consider the possibility of a major earthquake? Can earthquakes be predicted? The answer is no, but we're getting better. Now, in terms of death and destruction, a couple examples here. The 1906 San Francisco earthquake, famous because it's in San Francisco and therefore the west coast of the U.S. This 1906 earthquake and the resultant fire, we'll see why the fire became such a problem as it's related to the earthquake, how that fire killed 3,000 people. The 2004 earthquake in Sumatra killed over 300,000 people. The basic stats are over the last 100 years, over 13,000 people are killed each year due to earthquakes and earthquake-related disasters like tsunamis. What is an earthquake? To provide an answer, we need to look at the global forces that are at work. We need to think about stress. Stress is a force spread out over some given area. Strain is deformation as a percent of distortion. Strength is a critical value of cohesion, the ability of a material to stay together. Earthquakes occur where rocks are being stressed and they suddenly break along a new or pre-existing fault. Seismic waves are ground vibrations caused by rocks slipping along opposite sides of a fault. That's what we perceive as the shaking or the quake of the earthquake. Now here's a simple diagram of stress versus time with earthquakes superimposed upon this timeline, this chronology. So as stress increases, we're going to approach the rock strength of the local rocks. Once we exceed that rock strength, there's a rupture. In the case of a total rupture, the whole system is reset. It then requires the same amount of time to reach that local rock strength again, where that rock is going to become ruptured. Now, if we only relieve part of that stress, we're going to reset the clock, but only partially. Now it's going to take a shorter amount of time until we have total failure of the local rocks, total rupture. If we introduce some complexities like a change in stress from earthquakes or nearby faults, we can lengthen that amount of time. So we relieved some stress in this case, a small amount of stress, increasing the amount of time to reach the point of total failure again. This is going to change the rock strength ultimately because of this relief via a nearby fault or a change in the rock strength itself. That's going to tend to shorten the reactivation times. The earthquakes aren't going to be as powerful. They're going to occur more regularly. And although that's irritating because you have earthquakes more often, they're not as powerful, and therefore the devastation isn't as great. So it's better to have lots of small earthquakes than one big one. Why do these earthquakes occur? What is going on? Why do we have to deal with this? We'll start with the elastic rebound theory. We touched on that in the last diagram, where we have a fault rupture. This is going to be expressed on the surface of the Earth or exhibited on the surface of the Earth at a point known as the epicenter. As we talked about earlier in the course, epi means on top of, So on top of the center of the fault rupture is what epicenter ultimately means. The focus, on the other hand, is the actual point within the earth where the slippage occurred. So here's an example of elastic rebound. A fence was built prior to the earthquake of 1906. During the earthquake of 1906, the land was offset by this amount, and therefore the fence is offset by this amount. When I was 17 and got sent out to California for the science conference, we got a chance to go to this spot, this precise location, it's still there, and take a photo with a really bad camera that I had at the time, which is why you're not seeing that photo. This is something that's been well known, and it's really a tourist attraction now. There are a number of things like this that you can check out if you're in this part of California. So now let's take a look at an earthquake from the fault rupture perspective. Building a fence before deformation is going to result in a deformed fence. Building a fence after deformation results in a fence that looks straight because it is straight. That's going to change after the earthquake. So here we're going to consider the stress, and that's going to require a measurement of the distance of the rupture, the displacement along that fault. It's going to have an area of 15 kilometers by 120 kilometers in this example. The slippage is going to occur dominantly at the focus here within the Earth's crust, and it's going to be measured relative to its position on the surface, which is known as the epicenter. So at 0 seconds, the rupture begins at the focus, and it expands outward along the fault surface, sending out seismic waves in all directions. So we have an initiation here, a beginning of unzipping. So think of this as a zipped zipper. If your jacket is like mine, the zipper doesn't work very well. So it gets hung up, and you pull on it, and you wiggle it around, you pull on it, and finally it begins to unzip. As it unzips in both directions here, we have a propagation of seismic waves. The earthquake itself starts at the focus and spreads out from the focus. After 5 seconds, the rocks on either side of the fault start to rebound from their deformed state, so they're snapping back. At 10 seconds, the rupture progresses along the fault surface. This is going to reduce the stress and allow the rocks on either side to rebound. Seismic waves are going to continue to be emitted in all directions as the fault propagates. Subsequently, after 20 seconds, the rupture has progressed along the entire length of the fault. The displacement across ceases. The rupture may continue to propagate further along the fault beyond this particular segment. It can continue to unzip off into the distance in this direction and continue to unzip off in this direction as well. After the earthquake, the stress has been reset. The rocks are no longer stressed, and we start the clock again towards the next rupture, the next earthquake. This is a photo of the aftermath of the San Francisco earthquake. This is taken from Nob Hill, and it's overlooking what is currently the downtown area of San Francisco here, the financial shopping district area of San Francisco. Everything, just about everything, was burned to the ground as a result of this earthquake. After the gold rush years of the 1840s, San Francisco had become kind of the New York City of the West Coast. That's where the money was, that's where the people were, and it was wide open for investment in the West. Fortunately, in a really weird bit of good luck, a pair of brothers videotaped a trip down Market Street in 1906. This is just a few days before the earthquake. So it captures San Francisco as it was. These aren't actors, actresses. This is how people behaved. And you'll notice that traffic is a bit chaotic. We have horses and cars and trolleys and trains and people just randomly leaping in front of each of them. A bit like Bucharest, driving around in Bucharest today. So it was shot in 1906, just prior to the earthquake, and it was put on a train to send to New York City for development the day before the earthquake. So if that had not happened, if the earthquake occurred one day earlier, we wouldn't have this footage. Some of the more interesting commentary includes every single person is wearing a hat. Every man, every woman, every baby, every child is wearing a hat. I didn't notice that, but now I do. Also, another person said, "I've never seen so many people that had to cross the street at the same time." Now, just shortly after this was taken, the entire city was devastated. The earthquake knocked down many of the buildings. There was no earthquake code then. And what didn't fall down was burned down. When earthquakes occur, they not only knock buildings down, but they also tear down infrastructure. Power lines come down, gas lines rupture, water lines rupture. Now the streets are full of rubble, and there's no gas, there's no electricity, there's no water, nothing to fight the fires. So people are really on their own. They ended up dynamiting a bunch of the buildings to keep them from falling on people. That includes City Hall. And essentially the entire city was wiped out. About 227 to 300,000 people were left homeless out of the 400,000 estimated to have lived in San Francisco in 1906. So the city was truly devastated. What's really exceptional about this is we didn't know this film existed until about 4 years ago. What the Huckleberry Finn is going on in California to explain this earthquake? When we look at a map of the full coast of California, what we can see here is the San Andreas Fault, or what we'll call the San Andreas Fault for the purposes of this course. You'll notice that different portions of this fault are active at different times. Starting with the southern portion of the fault here, we have a magnitude 7.7 earthquake occurring at 1680 CE, or AD. Think of this as unzipping a long transform fault zipper. Starting here, we unzip to 1680. So the slippage has occurred. The rocks have been relieved of their stress. That induces more stress on this section. This section is going to unzip in 1857. With a magnitude 7.9 earthquake. Now, not on this map, but up here, there was an Owens Valley earthquake around, I think it was May or March of 1872, which had a magnitude similar to this, around 7.7, 7.9-ish. Very strong earthquake. Not many people were living there, so only about 27 people were killed. Then we reach a section of the fault that's known as a creeping segment. And here, we have more or less continual adjustments. Small adjustments, very, very small earthquakes occurring very, very often. And the net result is no large, catastrophic, destructive earthquakes. For reasons beyond me, no one really lives here either. It's got the same weather as LA and San Francisco, which is really good weather. No big earthquakes, but nobody lives here. San Luis Obispo is here somewhere, and Pismo Beach, down around here somewhere, but those aren't big population centers. We get out of this creeping segment, the safety zone, up to San Juan Bautista. And here we have another segment of stress buildup. This stress was relieved in 1906. So we're continuing the unzipping of California up to 1906. We have the magnitude 7.8 earthquake, which we just saw in the series of videos. And that brings us up here to Cape Mendocino. And here we see a curve in the fault. This leads to complications. Much like the San Gabriel Mountains down here in LA, they represent a bend in the fault. And this bend in the fault was activated in 1992 with a very large earthquake. So we've now unzipped California from the 1600s up to the 1990s. What's next? One of these segments is going to be active again at some point. They're all about due. Certainly the southern sections are closer to being due than northern sections, but there have been some adjusting earthquakes over the last few decades that have relieved some of this stress. When we look down from above, drone footage here, in Diagram A, we have a farmer building a stone wall across a right lateral strike-slip fault a few years after the last rupture. So the stress has been relieved, and we've reset the clock. The farmer builds a stone wall. Subsequent to that, over the next 150 years, these blocks are continuing to move. They're building up stress, and deformation is beginning to occur within this rock sequence. In diagram C, just before the next rupture, a new fence is built across the deformed land. In this case, we have a wooden fence going up. Now we're going to have the rupture. The fault is going to slip. This is going to drop the stress, and elastic rebound is going to restore the block to their pre-stressed state, so they're no longer internally twisted and distorted. Now what happens is the stone wall, which was straight in the first place, is straight again, but offset. The fence that was built across deformed land is offset as well, but because it was built on deformed land, it's going to retain that deformation in its structure, in its position here. Much like a barn that's about to collapse, I forget where this picture is from, the combination of gravity and wind have stressed this, and we're about to the rupture point. Sometime soon, the right amount of wind is going to hit this, maybe a snow load on the top, overstress this, and collapse. The earth will quake next to this barn. So what is an earthquake other than the shaking of the earth? Well, it's a local buildup and release of stress. And we can see that release of stress here in the destroyed roadway. It consists of foreshocks. These are small earthquakes that begin the unraveling, begin the breakdown of the fault, the release of stress. We have the earthquake itself, and then we have aftershocks. These are final adjustments of stress relief after the big earthquake. When we look at this in 3 dimensions, we see the focus of a large earthquake here. We're going to have foreshocks that are warnings that something big may be coming. Or you may just have some small earthquakes and no big earthquake for decades. That's a frustrating aspect of seismology. So we have adjustment along the main fault and along subsidiary faults that will be seen as foreshocks. During the earthquake, we have the big slippage starting at the focus along the main fault. This big slippage is going to generate the most energy or release the most energy and therefore cause the most damage. After the earthquake, we will have almost always a large number of aftershocks that occur on subsidiary faults and a little bit of slippage on the main fault. So you can think of this as watching popcorn pop. You got a couple kernels going off early, then about a minute or 2 in, you get the big blast. Lots of activity, lots of quaking and shaking, lots of popcorn kernels. Then it starts to slow down. This is where you make your judgment. Is it slow enough that I'm still going to get some popcorn? Or is it so slow that I'm starting to burn the popcorn that I already have? Make the call. How do we study these earthquakes? How do we evaluate what's going on within the earth that caused the earthquake and causes the damage and is going to result in a subsequent earthquake at some point in the future? We use seismographs. Seismographs are machines that record seismic waves generated by earthquakes. It's a graph that records seismic activity. They work in a number of ways. They measure vertical ground movement, how ground moves up and down, and they measure horizontal ground movement, ground shaking back and forth or wiggling back and forth. And the way they do this is different depending on whether you're measuring vertical or horizontal. For vertical displacement, we hang a mass on a spring. This mass is going to have some inertia. All objects will tend to maintain their station in space unless they're disturbed by something else. In this case, this object, the mass, is going to stay in one location as the Earth itself moves up and down around it. Because this mass is stationary, this rotating paper is going to record vertical movement. So as the Earth moves up and down, this recording pen is going to move up and down in response, and it's going to be spooled away and leave a permanent record on paper. This is the simplistic way that we measure vertical Earth movement. Now for horizontal movement, we have a mass that's on a hinge and some supporting structure here, a cable or a string. That's going to allow the mass to maintain station, to maintain one location in space as the ground moves back and forth beneath it. So this drum is also going to move back and forth along with this stand, this base, and the net result is the mass is going to leave a record of that horizontal movement on this rotating drum of paper.